Welcome to Joe. If you were not expecting, thank you. Goodbye.
Good morning, guys. So last time we had started talking about how to calculate the number of electrons in the conduction band and holes in the valence band. And we said that the answer comes in two parts, as shown by this integral over here. So for example, to calculate n, the number of conduction electrons, what we first have to figure out is the so-called density of states, n of E, where the meaning of N of E is N of E times dE is the number of available states in the conduction band between an energy E and E plus dE. So that's shown in this second column over here, where I'm plotting the density of states, N of E, on the x-axis as a function of electron energy increasing upward, okay? Now, the way to read this figure is I have four columns and 3 rows. On the left-hand column, I'm showing the band diagram. So EC is the bottom of the conduction band, EV is the top of the valence band. We know that the axes are position on the x-axis and electron energy increasing upward, while hole energy increases downward, okay? We said that at the conduction band minima, the electron only has potential energy, and as you add kinetic energy, you move up in the band all the way up to the top of the conduction band, which you can call EC top. Similarly, in the valence band, you have allowed states between EV, and as you increase hole kinetic energy, you move down all the way up to the bottom of the valence band. In between, you have forbidden states, which are called the energy gap. Now recall, however, that it's really a sequence of bands and gaps. So below the valence band, we'll have another gap, below which we'll have a completely filled up band, and so on and so forth. But those deeper lying states don't really play any role in semiconductors or chemistry for that matter. Similarly, above the conduction band, which is almost completely empty, but has a few electrons in them at room temperature, where the conduction band is the first excited state above the valence band. But then above the conduction band, you have other forbidden gaps and even more higher excited states, which are never going to be occupied by electrons, and therefore those are also not relevant, okay? The second row, the second column is the plot of the density of states. And here I'm plotting the density of states on the horizontal axis. Once again, the energy is on the vertical scale. So for each of these figures, I'm making the vertical axis energy so that I can kind of line up the various figures in terms of energy. The horizontal axes are going to be different. On the first one, in the first column, that's the position in the semiconductor. In the second column, it's this density of states. The third column is a Fermi-Dirac occupancy factor. And the final column is the number of electrons or holes. Electrons or holes, once again, plotted as a function of energy. Okay, so for each of these, the vertical scales are all the same. It's electron energy increasing upward, hole energy increasing downward, but the horizontal scales in each of these columns is different. The first one is position. The next one is density of states. The third column is the Fermi-Dirac occupancy factor. And the fourth column, which is given by this integral over here, is the number of electrons in the conduction band or holes in the valence band. You also notice that I have 3 rows of similar figures. The first row corresponds to an undoped semiconductor, which is known as an intrinsic semiconductor, where the numbers of electrons and holes we'll see are going to be equal. And these are the electrons and holes that are generated thermally by directly exciting electron from the valence to the conduction band. The next row is a semiconductor where I've purposely put in donor type impurities. And what you'll see is the main difference will be the Fermi level, which was sort of in the middle of the gap in the intrinsic case, moves up close to the conduction band, and that will lead to a larger number of majority carrier electrons and a corresponding decrease of the minority carrier holes compared to the intrinsic undoped case. In the intrinsic case, the number of electrons has to be equal to the number of holes. Conversely, if I make it p-type, the third row, the valence band we'll see moves closer to the valence band. The Fermi level moves closer to the valence band. And now I have majority carrier holes and few minority carrier electrons. So that's what we'll prove in the next few slides, okay? All right, so to get the number of electrons or holes, like I said, you have to do this integral. And physically, what does that mean? You first have to count the number of available states, right? Because so far we've told you that you cannot have any allowed states in the band gap. You're only allowed quantum mechanical states in the bands, in the conduction or the valence band. But I haven't told you so far how many states are we talking about, right? That information is given by this density of states, which itself is a function of energy, N of E. And the meaning of N of E is N of E times an energy increment delta E is the number of allowed states between an energy E and E plus delta E, okay? And that's shown graphically in this second column, okay? And we will prove, well, I won't prove it, I'll sort of make it plausible, that this is a parabolic shape, and that's why these are known as parabolic density of states. So what you find is, right near the band edge, you really have a low value of density of states. So you really have few allowed quantum mechanical states right at the band edges. But as you move up in the band, corresponding to increasing kinetic energy, you have more and more allowed energy states in a certain energy increment, dE. And I'm shading a region over here between E and E plus delta E. So whatever that area is of the shaded region is the number of allowed states between E and E plus delta E. You'll have similarly density of states in the valence band, okay? Now, the way to calculate the density of states itself is you actually first count states not as a function of energy, but rather as a function of the wave vector k, okay? What is the wave vector? Well, we saw that the wave vector is given by, k is given by 2 pi divided by the de Broglie wavelength, okay? And we said that the way you do that counting is you consider a particle in a box, say a rectangular box, as we did in chapter 2, okay, when we solved various problems of quantum mechanics. And we said that if you have a particle in a rectangular box, the first allowed wave, if you will, is half of a wavelength fitting within the box. Okay, so in that case, the first possible wavelength, lambda 1, is 2 times the length of the box, right? The next allowed wave is a full wave fits within the box. So lambda 2 is equal to L, and so on and so forth, okay? So what you'll find is for the nth state, Kn works out to n pi over L, where n are integer numbers. For the first ground state, n equals 1, the next state, n equals 2, and so on and so forth, okay? So the nice thing is, you find that the spacing of these allowed energy states in terms of the variable k, the wave vector, is uniformly spaced because, you know, n goes as 1, 2, 3, etc., times pi over L. Okay, so that's why it's convenient to first count allowed states as a function of k, because these are going to be equispaced in k space, okay? In this case, of course, we are looking at a one-dimensional problem. In general, we'll have 3 dimensions, kx, ky, kz, and what you'll have is you'll have the spherical volume of k space with equispaced allowed quantum states. Okay, so it's easier to count in terms of the k variable, okay? And this derivation, like I said, although I'm not doing it, is given in one of the appendices over here. And you might want to go through that, even though I'm not going to make you responsible for it in the exams. Now, what does this box physically correspond to? Well, in our case, this length of the box will correspond to the length of the crystal that I'm dealing with. So you'll find that if you have a longer semiconductor crystal, L becomes longer and the spacing between the allowed k states decreases. Okay, therefore you get more densely spaced k points. If the length of the crystal is smaller, L is smaller, the spacing between the k points is going to be larger. Okay, and that makes sense because for a longer box, a larger volume, you'll obviously have more allowed quantum states. For a smaller crystal, you'll have less allowed quantum states. So that's what this is due to. Okay. Now, once you've counted states, allowed states as a function of k, then you have to do a change of variables to energy. Okay. And what allows you to do that change of variables from k to energy is this EK relationship, which we determined in the previous lecture. And that, of course, is known as the band structure. Now, in the simple case, we see that in semiconductors or solids, the relationship E of k is a parabolic relationship, y equal to x squared is a formula for parabola. So here we see E varies as k squared. So that's the shape of a parabola. And we've seen these parabolic relationships in previous lectures. It's given by h bar squared, k squared over 2m star, where m star is not the actual mass of the electron, but it's a so-called effective mass. Nothing funny about this effective mass. Effective mass captures the interaction of the electron with the periodic crystalline potential in the semiconductor. Okay? And once I've taken that interaction into account in terms of m star, I can forget about this periodic crystalline potential, and I can think of the problem as the electron moving in free space, okay? And I don't have to worry about this periodic crystalline potential. Okay, so then I can look at this wave with a modified effective mass bouncing back and forth between the walls of the crystal itself, not the atoms themselves, but the entire macroscopic crystal. Okay. Question then, of course, is why the heck do I want to change variables in terms of counting density of states from K to energy? The reason you want to do that is the occupancy of the states is given by this third column over here, and that's this factor F of E, the Fermi-Dirac distribution function, which we discussed last time. And let me momentarily go back to the previous slides, where we said that the Fermi-Dirac distribution function is a quantum mechanical version of a classical Maxwell-Boltzmann distribution function, where we study that the occupancy of higher lying energy states scales as e to the power minus delta E over KT, where delta E is the energy difference between, say, the lower lying state and the higher lying state. Okay. So what this tells you is, as I go to higher and higher energy, the occupancy of these higher lying states decreases exponentially with energy. Now, what is this value of K over here? Is this the wave vector? Does anyone remember?
Which K are you pointing to?
K over here, e to the power minus delta E over KT.
This can't see where over here is.
Okay, so e to the power minus delta E
there
over KT. Okay, that K.
That would be the
Is that
Boltzmann constant.
Very good. So that's really the Boltzmann. Yes, it's not the wave vector. So let me write that as K Boltzmann. Okay. Too few letters in the alphabet. We need more letters in the alphabet. All right. So what he said was that's the Maxwell-Boltzmann classical distribution function, okay, which decreases exponentially, where the occupancy factor decreases exponentially with energy as you go to higher and higher energies. Okay. But quantum mechanically, you said that you have to replace that by this function f of E, which is given by 1 plus e to the power E minus a constant mu, which is known as your chemical potential or electrochemical potential. Think of it as a constant, depending on the problem at hand, divided by this KT, Boltzmann constant, plus or minus 1. Minus 1 in the case of integer spin particles called bosons. That gives you the so-called Bose-Einstein statistics, which will not be getting into our class. And the plus 1 corresponds to half integer spin particles called fermions, electrons being an example of that. That gives rise to the Fermi-Dirac distribution function. Now, the difference of plus or minus 1 is not very important for high energies, where E minus mu over KT is a very large number. So then both of these asymptotically match the classical distribution function, e to the power minus E over KT, because if E is much larger than mu, this first term becomes much larger than 1. So you can ignore the plus or minus 1, and you're back to e to the power minus E over KT in the numerator, just like in the classical Maxwell-Boltzmann distribution function. The difference shows up at low energies close to the chemical potential or at low temperatures. And there you see a huge difference between Bose-Einstein and Fermi-Dirac statistics. Basically, in the case of Fermi-Dirac, for energies E less than mu, you can ignore the first term, but you then end up with 1 over basically 1. Therefore, this asymptotically goes up to 1, meaning that the maximum occupancy of a state for fermions is 1, which is another way of stating the Pauli exclusion principle. Okay. This Fermi-Dirac distribution function we then plotted in a magnified version over here. Now I'm showing it not as a function of E minus mu over KT, which is sort of a normalized way of showing the energy, but I'm now showing it as a function of energy itself. The mu in the case of fermions is also known as the Fermi level. So that's the distribution function. So e to the power e minus mu over kt is now written as e to the power e minus Fermi level over kt plus 1. And the shape we plotted out for different temperatures. We saw then that at high temperatures or high energies at high temperatures, you have a function which looks like the Maxwell-Boltzmann distribution function, but at E equal to EF, so energy is close to the Fermi level, you get e to the power 0, which is 1 plus 1. So you have an occupancy factor 1. And energy is less than EF. The first term basically gives you e to the power minus infinity, which is 0 plus 1. Therefore, it asymptotes to 1, Pauli principle. Now, this Fermi-Dirac factor ranges between 0 and 1, but you should not mistake this for probability of occupancy. This is really the average occupancy of a quantum mechanical state, okay? But because in the case of fermions, it ranges between 0 and 1, people will mistakenly sometimes call it probability of occupancy, okay? And sometimes we'll also sloppily call it the probability of occupancy, but you need to be clear in your mind, it's not really the probability, it's the average occupancy of a state, okay? It cannot be the probability because then in the case of Bose-Einstein, we see that the f of e blows up. It can be much larger than 1, which probabilities cannot do, okay? Okay, so that Fermi-Dirac occupancy factor is this term over here, and that's shown in the third column. But now I'm replotting this f of e by turning the figure by 90 degrees so that the energy scale points upwards instead of horizontal. And I want to do that because in each of these figures, I want to line up the energy axes horizontally so that I can compare all these figures where, once again, the horizontal axes, of course, are different, but the vertical scales are all electron energy increasing upward, okay? All right, so once I have the average occupancy, what I need to do is I multiply the number of available states, N of E, as a function of energy, times the average occupancy of the states. dE will give you the number of states that are actually occupied by electrons between an energy E and E plus dE, okay? So then how do I get the total number of electrons? You simply have to integrate, right? Between the bottom of the conduction band to the top of the conduction band, which you can call EC top, okay? But because the Fermi-Dirac occupancy factor rapidly dies down to 0 with increasing energy, and for all practical purposes, it can replace the top limit by infinity, it really won't add to the integral, right? So it becomes simpler in terms of doing the integral, just replace the top of the conduction band by infinity, all right? Now let's see what the shape of this integrand would look like. Well, as you go up in energy, you see you have more and more allowed states. Therefore, this integrand, N of E times f of E, would tend to increase. But mind you, it's multiplied by this f of E, which is a decreasing function, almost an exponentially decreasing function. And pretty soon that exponential decrease wins out. And therefore you end up with a shape, which is like this. Let me clean this up a little bit. Okay, so you find that the number of electrons occupying different energy levels is obviously 0 in the band gap. It increases, it peaks at some point, and then it dies down. So you have very few electrons occupying these higher energy states, okay? Same with the valence band, holes in the valence band. The only difference being in the valence band, you have to multiply the density of states in the valence band, which I might call N sub V, times not f of E, but 1 minus f of E, because a hole is a missing electron. You guys with me so far? Now, in the case of an intrinsic semiconductor, we'll see that the Fermi level will be sort of in the middle of the gap. So as a result, this f of E function and how this exponential tail projects into the conduction band will kind of be the mirror image of the 1 minus f of E for the valence band over here. Not exactly, but sort of. And as a result, when you do these integrals, you'll get the same areas under these curves. So you have the number of electrons equal to the number of holes, and both will be equal to what's called the intrinsic carrier concentration, N sub I, which makes perfect sense because if in an intrinsic semiconductor, I don't have any dopants, the only way I get electrons and holes is by directly exciting electron from the valence to the conduction band, and that would create 1 electron and 1 hole, right? Equivalently, you can say that's breaking one of those covalent bonds, create one conduction electron, and leaves behind the missing state, which is a hole. Okay.
Really quickly, is the Y
Yeah.
term on those graphs E of F?
No, E of F is the value at this point. The Y term over here is
Okay.
energy.
What's the X term on those graphs then? Position?
So on the first column, it's position. So let me write it down. It's position in the semiconductor. Okay. The second column, it's density of states. The third column is F of E. Okay. And the fourth column is either the number of electrons as a function of energy or number of holes in the valence band as a function of energy. But for all of these figures, the vertical axis is energy increasing upward. Okay. So here also is energy increasing upward. Let me clean this up.
Okay, and when you jump from one part of that graph to the other, are you jumping just from like one area to the other area, or are you jumping to a point on that line? I wasn't sure if we were accounting for those in terms of like the total area or not.
Right. So no, we are looking at a particular position. Okay. I'm looking at a particular position. Okay. And at that position, I look at the number of allowed states as a function of energy, and that's what I plot over here. At some position, say X naught. Okay. At the same position, I see what the occupancy factors are as a function of energy. Okay. And then at that position, let me call it X naught, I can figure out how many electrons there are as a function of energy. Okay. So this second, third, and fourth columns all are looking at a particular position in the semiconductor.
Okay, so you have a set position like from the first graph,
Right.
but let's say I was doing like trying to associate it with position on the other graphs. It seems like, I mean, for the first two, you might be fine, but then for the last one, you could have a position that has 4 different points.
So for second, third, and fourth columns, they're all considered at a fixed position in the semiconductor. All right. So I'm calculating the number of electrons at some position X naught equal to 1.5 microns in the semiconductor. Okay. I think where you're getting at is next, you have to figure out what the electron and hole concentrations are as a function of position. Okay. And that will come later on. Here, I'm looking at a homogeneous situation because I'm showing the bands as being flat, right? The bands are flat, meaning that there's no electric fields. It's a homogeneous system. So no matter where I look, I'll get the same electron concentration and everything. All right. Now, later on, when you look at devices, we may have in a PN junction, for example, the bands varying as a function of position. All right. And then you may have a Fermi level like so. And then you get different number of electrons at different semiconductors. So you look at different positions and you see that the energy axes get shifted up and the number of electrons and holes at different locations will be different. But here we are starting out with the simplest case where everything is homogeneous. Okay. There's no electric field, therefore there's no variation of the electrostatic potential, and you get the same electron concentration everywhere. All right. So once again, I choose any position. It doesn't matter if it's a homogeneous system, it'll be the same everywhere. Okay. And at that position, I figure out how many allowed states there are as a function of energy. I plot that on the second column. Then for each of those allowed states, I find the average occupancy. That's my F of E, plotted as a function of energy. The product of the two gives you the number of electrons as a function of energy. That's this fourth column. And if you integrate that, that's the area under the curve. That gives you the total number of electrons at that location, X naught. Okay. I could do that at some of the locations, say X prime. Okay. I get exactly the same result because it's a uniform homogeneous system. On the other hand, if I do that later on, when I start looking at devices at different locations, for example, I might end up with different number of electrons and holes. Okay.
Okay, I think the one thing I was confused about is how you're actually transferring position from the first to the second graph. Like, are you doing it based on a 3-dimensional point or a 2-dimensional point, or is it just?
You could think of it as a 2-dimensional point if you want to. Yeah, you could think of it as a 2-dimensional point. Okay. So if you think of it as, you want to think of it as a 2-dimensional point, you may think of, say, position on one axis, say, okay? Energy on the vertical scale, okay? And then the horizontal axis could be your density of states or F of E. The problem is, and we have too many variables, right? We got position, density of states, Fermi-Dirac occupancy, and then finally the number of carriers, right? So you really need a 4-dimensional axis, actually 5-dimensional axis, right? Then you also have energy, right? So to really plot everything on the same axis, you need a 5-dimensional axis. You can visualize that, right? The most you can draw is a 3-dimensional axis, right?
Yeah.
So that's why I'm saying, don't worry about the dependency on position. I just look at a fixed position, all right? For each of these figures, I make the energy axis the vertical scale, okay? And then I look at different quantities, either position, N of E, F of E, or number of electrons, and I plot them on separate figures. But you could combine all of them if you could visualize the 5-dimensional axes, right? That's hard to visualize.
Okay.
Anybody else have confusions also? And if you have confusions, maybe you can chat offline, but if others are confused also, this is an important point. So I want to make sure that everybody gets this concept. Anybody else confused? All right, let's move on. And then, think about it. And if you still have confusion, by all means, call me up, okay, later on. Okay. These are good questions. All right. So hopefully you now see that what you have in the case of the intrinsic undoped semiconductor. And as I just said, for N-type, the Fermi level we'll see moves up. Therefore, this F of E term will be higher compared to the intrinsic case in the conduction band. And therefore, you end up getting a larger area under this curve corresponding to the number of electrons. But as F of E goes up in the conduction band, this mirror image figure, which is this 1 minus F of E, that tail will decrease in the valence band, okay? Because if I shove this FEF term to higher energies, that's what happens in an N-type semiconductor, this tail will become smaller, okay? And that's kind of what I'm showing in the next figure in a magnified form. So the intrinsic case corresponds to E of EF being more or less near the middle of the gap, and this F of E and 1 minus F of E terms are going to be kind of symmetric. But N-type EF moves up close to the conduction band. This F of E terms becomes much larger compared to the intrinsic case, but then there's a corresponding decrease of the 1 minus F of E term. Conversely, for P-type, 1 minus F of E goes up at the expense of the F of E term in the conduction band. Okay, so that's the third row over here corresponding to the P-type semiconductors. The final thing that, and this is repeating what I told you from last time, so when you do this change of variables from K to energy, you use this band structure, okay? And if you do the math as shown in this appendix, you'll get a density of states which will vary as E minus EC to the power half. So square root of E minus EC. So when E equals EC at the conduction band edge, I get density of states equal to 0. As I go to higher and higher energies, you find the density of state scales as square root of E minus EC. And that's also the shape of a parabola, because y equal to x squared is the formula of a parabola. But conversely, x equal to square root of y is also the shape of a parabola. Okay, so that's why this density of states is called a parabolic density of states. Now, if you take a graduate course, we'll see that realistic band structures are not always perfectly parabolic, as I showed you in a previous lecture. And you'll find that in a practical, realistic case, the density of states also will not be a perfect parabola. They have all kinds of funny, sharp features and things like that, but we won't worry about those in this class. All right, so this really is the most important figure, if you will, in this section. And the rest is working out the algebra of this integral, which looks horribly messy. I'm going to go through it quickly because I'm not going to test you on there. All that I really care about is a final answer, okay? So what does that integral for the N of E look like? So it's the integral of number of allowed states between an energy E and E plus DE times the average occupancy of the states So that'll give you the number of allowed states N of E between an energy E and E plus DE. Okay. So that's this N of E. And then to get the total number, you simply integrate N of E DE, right? That's the area under the curve in the fourth column over there. Okay. So then I simply plug in the expressions for the density of states, which is derived in the appendix, times the Fermi-Dirac occupancy factor, which is also derived in a separate appendix. You should look through that just to satisfy your curiosity. And then this integral, obviously, is a somewhat complicated integral. What you do is you simplify the thing first by looking at the situation where EF is deep in the band. Okay, so in the middle of the gap, or even if it's close to the conduction band or the valence band, it's several kT away from that, several times the thermal energy away from the band edges. Under those conditions, you can simplify this Fermi-Dirac distribution function by the corresponding Maxwell-Boltzmann approximation of it. So f of E, you can ignore the +1 term over here and it becomes e to the power minus E minus EF over KT, or equivalently write that as e to the power EF minus E over KT. Okay, so this is approximated by the Maxwell-Boltzmann term, which is only valid if the Fermi level is far away from either band edge, conduction or valence band. What does far away mean? It's several kT away from that, roughly 3 to 5 kT or more away from the band edges makes this a good approximation, all right? Now, in some cases, the doping may be so high that the Fermi level will be very close to either the conduction or the valence band. Such high doping levels are called degenerate doping, in which case the expressions that I'll derive will not work perfectly, okay? But I'll not worry about those in this class. If you take a graduate class, you talk about those extreme doping limits and things like that. All right, so once I've simplified the Fermi-Dirac term by this exponential term, then you can introduce new variables to do the calculation. So you write E minus EC over KT as a new variable, what you call eta, okay? And then you also introduce another variable. I guess this is not eta, I think that's called, in my knowledge of Greek is pretty rudimentary. I think that, does anyone know what that symbol is called? Maybe it's epsilon, okay?
It looks like zeta.
Oh, zeta,
Thank
okay,
you.
all right, thank you. I think that this one is eta, okay? So eta is written as another scaled variable. So E minus EF, okay? I write as E minus EC. So this E to the power EF minus E over KT, I can write as EF minus EC plus EC minus E. Okay, I haven't changed anything, okay? And then I rewrite these in terms of two variables, okay? So E.
I think the symbol is psi, just
Okay.
like xi, just because it has the second
Okay.
curve on top. But that just
Okay.
might be stylistic.
Okay, that's fine. Okay, so and E minus EC, E minus EC, I've written as xi, I guess you told me, right? And then EF minus CC is this new symbol eta, okay? Both normalized with respect to KT, okay? Don't worry too much about this integral. I'm just showing you the steps, okay? Even though you'll not be responsible for all that. All that I care about is the final result, okay? So when you do this very, very complex integral, these, by the way, are known as Fermi-Dirac integrals of order half. The final result that you get, and that's really all that you'll be responsible for in this exam, in this course, is this expression over here, okay? So that's the result of this integral. It's not a very complicated integral. I mean, if you feel like torturing yourself, spend the weekend actually working it out. So the final result is this, in terms of a whole bunch of constants, notably the effective mass, but now notice that I'm calling it the density of states effective mass, Boltzmann constant K, this is not the wave vector K, T in Kelvin, so you always use Kelvin, divided by H squared, this is Planck constant square, not reduced Planck constant H bar, H square, e to the power minus EC minus EF over KT. So that's the result of this integral. Okay, I want to see what it physically means. Okay, but first of all, this e to the power minus EC minus EF over KT, I write as a Fermi-Dirac distribution function evaluated at EC, at the conduction band edge. What does that mean? Well, this is the Fermi-Dirac distribution function in the limit of Fermi level much far away from the band edges, okay, where E minus EF is much greater than KT. So under those conditions, I was able to approximate this Fermi-Dirac term by this exponential term, right? And then if I evaluate this occupancy at E equal to EC, I put E equal to EC over here, okay? So that's the occupancy factor at the conduction band edge. So this term over here is the occupancy at the conduction band edge. What does that mean? It means I look at this Fermi-Dirac distribution function and I figure out what the occupancy is at the conduction band edge. So now I'm not looking at as a function of energy, I'm calculating the occupancy at the conduction band edge, okay? So that's this term over here. And everything else is a constant, which I call the effective density of states in the conduction band, N sub C. Now, what does that mean? What do I mean by an effective density of states? The effective density of states is taking this density of states N of E and mapping that to the conduction band edge, okay? Such that this highly complicated integral can be written as a constant, which is this effective density of states, which will depend on the type of semiconductor I'm dealing with, times the occupancy at the conduction band edge. Let me ask you a question. Am I saying then that this effective density of states is simply the integral of the density of states? Am I just integrating this density of states and I'm calling that the effective density of states? Am I looking at this N of E curve and simply figuring out the total area and calling that the density of states, or is it a more subtle definition? Notice what I'm doing. In this integral, I take the density of states and weight that by the occupancy factors, okay? So what that means is a state which is at a higher energy, should I count that as heavily as a state at a lower energy? Or they counted with different weights? The answer to that is given in this third column over here. Anybody? In terms of calculating this integral, should I count these allowed density of states the same for all energies, or should I weight them differently?
The higher energy ones would be weighted less.
Very
Their
good.
occupancy factor is lower.
Excellent. Very good. Okay. So as you correctly pointed out, and as shown in this third column, the higher up you go in energy, notice that this F of E term dies down rapidly, right? So a higher energy state has a lower occupancy factor than a lower energy state, right? So when I'm doing this integral, I basically weight the higher lying energy states with the lower occupancy factor than energy states lying close to the conduction band edge. That's a key point. So when I introduce this concept of effective density of states, I'm mapping this energy dependent density of states N of E to a single number at the conduction band edge, and I call it N sub C. So it's sort of like a delta function density of states. This whole distribution as a function of energy is mapped to a single number NC at the conduction band edge times the occupancy factor at the conduction band edge. That's my F of EC, okay? So I've sort of compressed all these complicated energy dependencies to a single number NC at the conduction band edge times the occupancy at the conduction band edge. That's really what I'm writing in this expression over here, sorry. This expression over here. So I'm writing this integral as a single number NC, the effective density of states, times the occupancy at the conduction band edge. But this effective density of states is the weighted sum of N of E weighted at each energy by the occupancy factor, mapped to the conduction band age. This is a very important concept, okay? I want to make sure that you guys are on board. So once I get that, I no longer have to fool around with this complicated integral every time I give you a problem involving calculating numbers of electrons or holes in a semiconductor. So clearly that's a huge simplification, right? Because this NC in the conduction band or N sub V in the valence band are constants depending on the type of semiconductor. Why does it depend on the type of semiconductor? That's because of this density of states. And we've seen already that the density of states is different in different semiconductors. Not sorry, the effective masses are different in different semiconductors. Everything else is a constant. Pi, of course, is a constant number. Boltzmann constant is a constant. Oh, T. So it would also depend on temperature. So it depends on the type of semiconductor and depends on the temperature. Planck constant is a constant. Okay. The occupancy factor of the conduction band age would also depend on temperature. Okay. So this N of E is obviously going to be a strong function of temperature. Sorry, this N naught is going to be a strong function of temperature. For the valence band, similar results, except that instead of F of E, I'll have to multiply by 1 minus F of E. So now I get an effective mass in the valence band times e to the power EV minus EF over KT. So you'll see that you have a change of sign. So in the conduction band, it's minus EC minus EF over KT, while in the valence band, it's plus EV minus EF over KT. Okay, so that's sign change over there. So this is nothing but the effective density of states in the valence band times the occupancy factor by holes. Okay, so let me repeat that again because it's so important and because I will give you problems in the exams, either the midterm or the final. So we calculate the number of electrons, say in the conduction band, by figuring out the number of allowed states as a function of energy. That's my density of states between energy E plus delta E. Multiply those allowed states by the occupancy factor F of E, which is also a function of energy. That's my third column over here. The product gives you this fourth column, the number of electrons occupying different energies. It has this hump as shown over here. And then to get the total number of electrons, you simply have to calculate the area under the curve, which is the area under the curve, and that's this integral over here. And the way you do that is you integrate this horrible looking integrand, okay? And the result of that is written in this very compact fashion, effective density of states, N sub C, which is this density of states, parabolic density of states mapped to the conduction band age. And when I say mapped, I don't mean integrating all these density of states and calling that the effective density of states. Instead, I weight the allowed states by the corresponding occupancy factors. So as someone correctly pointed out, higher lying states count less heavily than lower lying states. So that weighted sum is what I call my effective density of states, times the occupancy factor no longer as a function of energy. I multiply that by the occupancy factor F of EC at the conduction band age. So that's also a single number, okay? So the result of that integral is written as a product of two numbers, the effective density of states, which is dependent on the type of semiconductor and the temperature, times the occupancy factor, which once again depends on the type of semiconductor and the temperature, and the doping level, because the Fermi level we'll see depends on the doping level and the doping type in the semiconductor. So this is a very important result, and this is an important result for the holes. Once you have that, you can use these and massage the expressions for other very, very important expressions that we'll be using all the time in this class, okay? So let's rewrite the density, the number of electrons in the conduction band as this, which is my N sub C, times this, which is my F of EC, okay, as shown over here. And that's expression for holes. Now, let's plug in the value of the Fermi level corresponding to no doping, the pure intrinsic semiconductor. When you have doping, you call it an extrinsic semiconductor, but no doping, you call it an intrinsic semiconductor. And under those conditions, the position of the Fermi level is given a special name. It's called the intrinsic Fermi level, okay? So if I have no doping, the number of electrons in the conduction band is created by directly exciting carriers from the valence band across the energy gap into the conduction band. How does it get excited? It gets excited by absorbing energy from the ambient. We are constantly bombarded by photons, infrared photons that you may not be able to see. These are, these heat waves having an average energy of, say, kT, the thermal energy. And then a few of those photons might get absorbed and they can excite electron from the valence to the conduction band, or equivalently, they can break some of these covalent bonds. In this process, of course, every time I create a conduction electron, you have to have a corresponding valence hole, right? So that's why Ni must equal Pi under intrinsic conditions, okay? To get those values, I simply, in this expression for N naught, I replace EF by EI. So I end up getting this expression. So you get e to the power minus EC minus EI over KT times the effective density of states. Same for the holes, but there's a sign change. It becomes minus EI minus EV over KT times N sub V, okay? Now, once I have these expressions for the intrinsic case, you can rewrite the expressions for the doped case in another form. So you can either write it as NC times F at EC, okay? Or you can rewrite in this form. You can write N naught as NC e to the power minus, I'm rewriting this exponent over here, minus EC minus EI plus EI minus EF, okay, over KT. Okay, I haven't changed anything. If I subtract and add EI, it's the same thing, right? But then I group these terms differently. So this term over here, NC e to the power minus EC minus EI over KT is nothing but NI. So I rewrite that part as NI, and what's left over is e to the power EF minus EI over KT, or minus EI minus EF over KT. So that's the second term over here, okay? So I haven't really changed anything. I'm rewriting this value of electron concentration in a different way as Ni e to the power EF minus EI over KT. While in the first version, I write it as NC times e to the power minus EC minus EF over KT. Now, graphically, what I've essentially done is, if I look at EC, EV, the EI will be sort of in the middle of the gap. We'll see in a second that it's not exactly in the middle of the gap. And then suppose that I'm looking at an N-type doped semiconductor, you'll find that the Fermi level will be in the upper half of the band gap. So basically what I'm doing is, in the first version, I'm looking at EC minus EF. So I'm looking at this energy separation, and I'm writing the electron concentration in terms of EC minus EF over here. That's basically what I've done over here, EC minus EF. In the second version, I'm calculating the result in terms of Ni times EF minus EI. So this energy separation, EF minus EI. Okay, so I'm just choosing different reference points, if you will. So if I reference the Fermi level with respect to EC, I have to use N sub C. If I reference the Fermi level with respect to EI, I have to use N sub I. And both of these expressions are very, very useful for calculating carrier concentrations. Okay. Same thing you can do for the holes. Okay. I get P naught equal to either NV times this. So here I'm measuring the Fermi level with respect to the valence band, or suppose I'm looking at a p-type semiconductor. Here the Fermi level will be closer to the valence band. Okay, so I could measure the Fermi level with respect to EI, as shown over here, or with respect to EV, which is the version shown over here. Okay. Now this expression for N naught and P naught in terms of EI gives you another very, very useful relationship. What do I get if I take the product of N naught times P naught? Well, multiply the right-hand sides. I get Ni times Ni squared. And how about the exponents? Well, for the first one, I get e to the power EF minus EI over KT. Well, for the holes, I get minus EF minus EI over KT. So when I take the product of the two, you find that this exponent will cancel with this exponent. And all that I'll be left with is N naught P naught equals Ni squared. That is a very useful relationship. And it's known as the law of mass action because it turns out in chemistry, you have similar expressions. When you react to different components, the concentrations of the constituents have a very similar chemical expression. So that's why this is known as the law of mass action. Okay. Essentially, what it tells you is, as I change the doping, suppose I go from N-type to P-type, we'll find that the Fermi level will move closer and closer from the conduction band edge towards the valence band edge. Okay. When it's close to the conduction band edge, I'll have a lot of electrons. Those are called majority carrier electrons in an N-type semiconductor. And I'll have very few minority carrier holes. That's called minority carrier holes. Okay. Conversely, as I move the Fermi level closer to the valence band by doping it with more and more acceptors, I'll increase the hole concentration. That'll become the majority carrier, but there'll be a corresponding decrease of the electron concentration. And in each case, the NP product will be the same. And that's exactly what I saw in this figure. So in the intrinsic case, N equals P, both equal to Ni, the intrinsic carrier concentration. In N-type, the Fermi level moves close to the conduction band, N goes up, but there's a corresponding decrease of the minority carrier holes. In P-type, the Fermi level moves closer to the valence band, now P goes up, and corresponding decrease of the minority carrier electrons. Okay. So this expression, this is an important slide for doing calculations. This expression in terms of the effective density of states and occupancy at the conduction band edge, or these expressions in terms of the intrinsic carrier concentration will be used again and again to solve math problems. Okay. Now, one final teaser, if you will, well, two final teasers. This effective mass that I'm showing over here for the conduction band, or similarly for the valence band, I'm denoting as m star density of states. Now, earlier, of course, in earlier lectures last week, we had already introduced the concept of effective mass, right? And remember, we said that this effective mass m star is nothing but the curvature of this parabola, right? So when I plot E of k, we're running out of room over here. Let's plot E of k over here as a function of k. We got the conduction band, valence band, and if E of k equals h bar squared, k squared over 2m star, we saw that m star was equal to h bar squared divided by second derivative, d2e dk squared. If you look back at your notes, you'll see that, right? And this is nothing but what's called the curvature. So if I had a band structure like so, and another band structure like so, that's case one, that's case two, who can tell me which semiconductor has a lower effective mass? One or two?
Two.
Very good. Okay. Now, the problem becomes in a semiconductor, in a crystal, of course, you have three different axes, right? Here, I'm just showing a one-dimensional case, but in general, we showed in a previous lecture. Let me scroll quickly through it. Yeah. Remember when we showed realistic band structures, E of k? These are parabolic, but not exactly parabolic. Okay, and we pointed out at that point that in different directions for different k values, you can have different EK shapes. So as a result, you end up getting different masses along the x-axis, y-axis, and z-axis. So you get an mx, my, mz, depending on the curvatures along the x-axis, y-axis, z-axis in a crystal, okay? Now that introduces a problem then, right? Because if I have different curvatures in different directions in a crystal, which of those masses should I use in this conduction band density of states, right? So here I have a mass that I use in this density of states. Which of those masses, mx, my, mz, corresponding to the curvatures along the x, y, or z axes, should I use over here? Well, the answer is you should use the geometric mean. So if I have three different curvatures, mx, my, mz, you take the product of the three and you take 1/3 cube root of that. Okay, so that's this m star over here. So that is nothing but the geometric mean of the three band curvature masses. Okay, so you take the geometric mean to get the density of states effective mass. Now in next class, we'll introduce yet a third effective mass, That's called the conductivity effective mass, which is used for calculating currents and all that. And there you can see that you have to use the harmonic mean. So things get pretty hairy. I'll summarize all of this in the next lecture, okay? So for now, you see that you start with the band structures. From the curvature, you get the starting mass, which is the band curvature effective masses. And then to calculate density of states, which is used for calculating electron or hole concentrations, you have to take the geometric mean of those band curvature masses. In the next class for conduction, we'll see you have to take the harmonic mean of the effective masses. I'm sorry, there's so many masses floating around. So I'm sure your head's spinning, and it's pretty confusing when you see it for the first time. One final teaser, and this is for chapter 4. We'll discuss non-equilibrium carrier concentrations. What does that mean? Well, in a semiconductor, if you dope the crystal with donors or acceptors, you get a certain number of electrons or holes which stay put, and that's called the equilibrium carrier concentration. That's what we discuss in chapter 3. In chapter 4, we'll move to what are called non-equilibrium scenarios, where you actually apply voltages to a semiconductor, or you shine, say, a laser beam and you excite additional electrons and holes. And there we'll see that this Fermi level EF gets modified by a new term, which is called the quasi-Fermi level, or IMREF. And we'll modify these expressions in equilibrium to non-equilibrium expressions in chapter 4. Okay, this is just a teaser. So when I talk about these in chapter 4, I'll refer back to this. Okay, let's tie up a few more loose ends in terms of carrier concentrations. Okay, the first loose end is this concept of doping compensation. What does that mean? And so far, I've talked about doping a semiconductor with donors, say with the concentration N sub D, or acceptors with the concentration N sub A. What if you did both? Maybe in a semiconductor, I put in 10 to the 20 donors per centimeter cubed, and maybe 2 times 10 to the 20 acceptors per centimeter cubed. Okay. So the question arises, would I then get 10 to the 20 electrons and 2 times 10 to the 20 holes? Because remember, each donor gives rise to an electron and each acceptor creates a hole, right? The answer is no. If I have both types of dopants, there's a cancellation effect, and the majority and the dominant doping type will win out. And basically what will happen is these electrons that are created by the donors, normally they get excited into the conduction band, but they see that they have acceptors down below, and they can simply fall down into the acceptor states. And it's only the difference between the two that will show up. Well, I guess in this figure, I had more donors than acceptors. So let me change the numbers. So I call it 2 times 10 to the 20 donors, say, and 10 to the 20 acceptors. Okay. So then out of the 2 times 10 to the 20, half of them fall into this acceptor states. And the difference, which is 10 to the 20 also, say, give rise to conduction electrons. Okay, so this effect is known as doping compensation effects. All right. Now, the way you solve problems of this type is by writing an expression of this form, which equates the total number of sorry. Hello? I hope it's not one of you. I think the audio is fine and video is fine. Okay, so anyway, so when I have both types of dopants, what you do is you write the total number of negative charges in the semiconductor. Hello? Hello? Hello. I'm in a class. I thought we were going to talk at 12. I can't talk right now. I'm in a class right now. Sorry. Yeah, so what I was saying is when you have both types of dopants, say, you equate the total number of negative charges to the total number of positive charges, okay? And that is a principle known as space charge neutrality. What does that mean? Well, in a semiconductor, we saw that if you introduce a donor type impurity, the fifth electron is donated to the crystal and it leaves behind a positive donor charge, right? Where the donor could be, say, an arsenic ion, okay? Now, the question arises, what is the net charge in the semiconductor? Well, the net charge is clearly zero, right? Because if this fifth electron from the valence band of the arsenic donor impurity is donated to the crystal, yeah, I create a negative mobile carrier, but I leave behind a fixed positive donor impurity, right? And the sum total of the two is equal to zero. So that's this concept of space charge neutrality. Similarly, if you have an acceptor such as boron that accepts electron, creates a positive hole, the net charge is equal to zero, right? So that's what I'm basically writing over here. I add up all the possible negative charges, which are these mobile conduction electrons, plus negatively charged acceptors, which are not mobile. Remember, the donors and the acceptors are locked in the lattice, equal to the mobile holes, P, plus donor impurities, which are not mobile. They're locked in the lattice. Okay. And once I have that, and in general, like I said, you could have both acceptors and donors in a semiconductor. All right. The second equation you use is this N times P product equal to Ni squared, which I derived in the previous slide. So the NP product equals Ni squared, so that you can get a quadratic equation either in terms of N or P. So if I want to work in terms of N, for example, I can then write N equal to P, which is Ni squared over N, plus I bring this over to the right-hand side. So that's the net donor concentration in excess of the acceptor concentration. So in this particular example, I had 2 times 10 to the 20 donors. That was my ND, and 1 times 10 to the 20. So ND minus NA would also be equal to 10 to the 20. So that's this term over here. Okay. Now notice this is nothing but a quadratic equation, right? Because if I bring this N to the left-hand side, I'll get N squared equal to Ni squared, which is a constant, times ND minus NA times N. And hopefully remember how to solve quadratic equations, okay? Now, in cases where the level of the net doping is very, very much larger than the intrinsic carrier concentration, then you can simplify this quadratic equation and you can write N as approximately equal to the net doping concentration, because if ND minus NA is much, much larger than NI, the first term becomes negligible, okay? So then N becomes roughly equal to the net donor concentration. And then once I get N, I can make use of this expression to calculate the minority carrier hole concentration, which would be Ni squared over N. So if I give you problems of this type, you first need to figure out if my doping concentration is much larger than the intrinsic carrier concentration. If it is, then you can use the simplified version. But if the net doping concentration is comparable to the intrinsic carrier concentration, you have to solve this full quadratic equation, okay? Now, one final comment about this business of space charge neutrality, which is what I used to write this expression down, okay? Because by space charge neutrality, I said that if you consider any macroscopic volume of the semiconductor, the net charges would be zero, right? And that's why I wrote the net negative charge, mobile conduction electrons, plus fixed acceptors equal to the mobile holes in the valence band, plus fixed donors. That's the basis of the statement, space charge neutrality. And it turns out this principle is not an universal truth. So it's not a law of physics like, the speed of light is constant in vacuum and things like that. This is an approximate law, which is only true if I have a semiconductor which is homogeneous, as for example shown over here. So if I have a situation where there's no, let me ask you, looking at this band diagram, can anyone tell me if the electric field in this case is 0 or non-zero?
Would we say non-zero because they're not equal on the top and the bottom?
No, that's not right. Remember we said that the,
bands are flat, right?
yes, exactly.
No.
If the bands are flat, it's 0. Why is that? Well, electric field is equal to minus dV dx, where V is your electrostatic potential, and then the conduction band edge is equal to the charge of the electron times V, okay? While in the valence band, it's plus Q times V, all right? So what this shows is, over here, V of x as a function of x is constant. EC is shown as being horizontal. See, V is constant, and I take the derivative of that, I'll get E equal to 0, right? On the other hand, if the bands were varying, there would be a constant electric field. If the bands had different curves, different slopes, that's a case of varying electric field. That's the most general case, okay? I'm also assuming in this particular case that the doping concentration as a function of position is constant or nearly constant, and then you can apply space charge neutrality. On the other hand, if there are varying electric fields, or if I change the doping as a function of position rapidly, then space charge neutrality breaks down. So this is not always true. It's only true in a homogeneous or more or less homogeneous situation, okay? And that's what I'm assuming for now. But later on, we'll modify the picture and we'll see what happens when things vary in terms of doping as a function of position, or electrostatic potential varies as a function of position in a p-n junction, for instance. All right, so there are a couple of other useful expressions that you can derive based on, for example, this NP product equal to Ni squared, okay? So what you can do is you can replace both N and P. Oh, by the way, I'm showing this as N naught, P naught in this particular case, implying that I'm looking at the equilibrium case, okay? Equilibrium means no carriers generated by, for example, a battery hooked up to the device, or no carriers generated by shining photons onto a semiconductor with a laser. So that could create additional electron hole pairs. Okay, so I'm not looking at such non-equilibrium scenarios. That's going to be discussed in chapter 4. Okay, so here I'm looking at an equilibrium scenario where the numbers of electrons and holes are just dictated by the doping levels. And if I let the system, if I let the semiconductor just sit there, the carrier concentrations are not going to change as a function of time. Okay. Under those conditions, we proved that N naught equals N sub C times e to the power minus EC. So we showed that N naught was equal to N sub C e to the power minus EC minus EF over KT. Okay. And P naught was N sub V. You change the sign, EV minus EF over KT. We proved that in a previous slide. Okay. Then you take the product N naught P naught. Well, one expression was product equals Ni squared, or in terms of NC and NV, you can write Ni equal to, on the left-hand side, you take the products, you get NC times NV, e to the power minus EC minus EV over KT. The EF terms will cancel out, okay? But what's EC minus EV? EC minus EV, what is that equal to?
The band gap energy.
Very good. That's a band gap of energy, okay? Now that's Ni squared. So if I take the square root, I'll end up getting square root of NC times NV, e to the power minus EG over KT. When I take the square root, I get the factor of 2 over there, okay? So that's a very useful, interesting relationship. Now let's see, if I plot it out for different semiconductors, what will I get? Well, what I do is, instead of plotting Ni, I plot Ni on a log scale, or equivalently, I take log of Ni. Now, if I take log of Ni, I'll get log of square root of NC NV, okay, which depends on the type of semiconductor and the temperature, of course, but relatively weak dependence on temperature, because remember, NC and NV depend on temperature to the power 3/2. On the other hand, this is a much stronger dependence on temperature, because that's an exponential dependency. So I take log of Ni, it's log of square root of NC/NV, which is a weak function of temperature, plus log of this exponent. So I simply get minus EG over 2 KT. So now if I plot log of Ni, or equivalently I plot Ni on a log scale as a function of 1 over temperature, I should expect a straight line whose slope would be given by Eg over 2K, right? And that's what I see in this plot. For different semiconductors, I have different band gaps. Silicon has a band gap of 1.1 EV, germanium is 0.67 EV, gallium arsenide is 1.43 EV. So higher the band gap, the steeper the slope, okay? Now, particularly interesting temperature, of course, is room temperature, which is 300 Kelvin. And you find that in silicon, you have a Ni, or intrinsic carrier constellation, of 1.5 times 10 to the 10 per centimeter cube, either electrons or holes. That's my value of Ni. Germanium with a lower band gap has a much higher Ni, as you'd expect. Gallium arsenide has a lower Ni, okay? As a historical aside, I point out that the first transistors are actually made in germanium because those crystals could be grown at a lower temperature more easily than in silicon. But because of the fact that the intrinsic carrier constellation is 3 orders of magnitude higher, approximately, a germanium transistor inherently will be 3 orders of magnitude leakier than a transistor made in silicon. Okay? And that pretty soon, once engineers realized that, they said, no, silicon is a much better semiconductor choice than germanium. Okay? And plus, of course, silicon is a lot more plentiful in the Earth's crust. The Earth's crust is about, I think, 25% silicon in the form of, rocks or sand and things like that. Germanium is a much more rare element, much more expensive. Okay, silicon has another key advantage, and that is, we'll see in chapter 5, you can grow silicon dioxide by reacting that with silicon, where silicon dioxide is an insulator, and this interface between silicon and silicon dioxide is one of the best electronic interfaces that you can have. You cannot grow such an insulator interface on top of germanium. And based on that, you can make things like MOSFETs on silicon, where you can make a gate, source, drain, with a very nice interface in between. So those are the 3 reasons. Silicon is more plentiful and cheaper. The higher band gap gives you a lower intrinsic carrier concentration. And then in chapter 6, we'll see you get a better interface with silicon dioxide. That's why silicon is king in terms of microelectronics. All right. Now, the other expression that you can derive is the second one over here, and this is very straightforward algebra. So all that I need to do is I write this expression for Ni in terms of EI and PI in terms of EI. I set the 2 equal to each other. I can evaluate an expression for EI simply by setting the 2 equal to each other. I'll let you do that on your own. And you'll see that is equal to EC plus EV over 2. Now, what is that? EC plus EV over 2 is exactly the middle of the gap, okay? But then we'll find that there's a second term, which is the ratio of NV over NC, which depends on the density of states in the valence and the conduction band. So if the bands are symmetric, where MV, the mass in the valence band, equals mass in the conduction band, NV would be equal to NC. So I'd get log of 1, which is 0, in which case the EI would be exactly in the middle of the gap. But in general, NV and NC will be slightly different, and you'll find that the EI will be biased just a little bit in favor of the lower lying density of states. And that makes sense, right? Because if you have a much larger density of states in the conduction band and a lower density of states in the valence band, to make Ni and Pi equal to each other, you have to sort of bias the thing a little bit in favor of the weaker band. So that's this expression over here. But for most purposes, you can assume that the EI is roughly in the middle of the gap. Okay, you can kind of ignore this correction term over here. Now, the Ni has a strong dependence on temperature. So what does it tell you? As you heat up a semiconductor more and more, regardless of the doping, you'll create exponentially larger numbers of carriers. And at some point, these thermally generated carriers will overwhelm the carrier concentration due to doping. Okay, and that's what's shown in this final figure over here. So here I'm plotting the carrier concentration as a function of 1 over temperature. Okay. And I've chosen a semiconductor doped 10 to the 15 n-type, say. Okay. So if I'm in this intermediate temperature range, you'll find that you get a carrier concentration given by the donor concentration of 10 to the T, all right? But as I make the temperature higher and higher, T becomes larger, 1000 over T becomes smaller. And not only do I get the carrier concentration due to the donor impurities, but now I start creating more and more electron hole pairs by directly exciting the valence with conduction band. And that term increases exponentially with energy, e to the power minus Eg over 2 kT, right? And at some point, the thermal generation of carriers will overwhelm the carrier concentration due to doping. Conversely, if I go to very, very low temperatures, even though this separation of the donor level is very, very small, if kT is made smaller and smaller and smaller, these carriers created by the donor fall back into the donor level. That's called carrier freeze out. So you're freezing out these conduction electrons back into the donor level, okay? In other words, if I have an arsenic impurity, donor impurity, normally the 5th electron would have been donated to the crystal, but now at low energies, it gets bound back into the arsenic atom itself. The carrier gets frozen out. And the question, which temperature range do you think my integrated circuit should operate properly in range 1, 2, 3, or all of these above?
I think it would be 2.
Very good. Because when I make my transistor, I carefully put in different types of dopings, right? I mean, in the source, drain, channel region, and so on and so forth, right? But if I heat up the semiconductor device so much that it flood everything with carriers thermally, right? Or if I lower the temperature by putting an IC in outer space where these carriers are frozen out, I don't get the functionality corresponding to what I designed, right? So transistors or ICs will only operate in a certain temperature window. Too hot or too cold, they start failing. That concludes our discussion about carrier constellations. Normally, I would have gone through some worked out examples. Because we've lost some lectures, unfortunately, we'll have to skip those. But hopefully, you can look through the worked out examples on your own. And if you have questions, by all means, you can ask me. Okay. So tomorrow, not tomorrow, on Wednesday, we'll discuss the business of transport. Now that we have figured out how to calculate carrier concentration, we need to see how they respond to electric fields, which is a mechanism called drift currents. Okay. See you on Wednesday. Any questions?
Thank you.